Good morning, folks. Well, morning at this end. Let's see, this time around, I want to talk about structures or records or whatever the language happens to call that kind of an idea, the notion of a C style of struct. So, as usual, we want to go through the operations supported, the implementation ideas, some of the implications of what you choose to do in terms of implementation. So, let's get started here. Let's get rid of that. Let's see. For our records or structures, the idea is we need some way, unlike arrays, to group together a bunch of different data types, lump them all together, and to be able to refer to them as a cohesive unit. Right? This lets you do a sort of top-down design of your data structure the same way as you would with your functionality, where you decide, okay, well, I'm going to have information about a university, and that's going to be composed of information about courses, and courses are going to be composed of information about assignments and about projects and about whatever else. And so you've got all these different sort of layers of data type. Each of them you can refer to by the name, right? The name for your record or your structure. And then they'll each have a bunch of different data fields. And again, they can be of any type. You've had lots of experience with using this kind of thing with structs and whatnot. And again, it's very similar to the idea that's incorporated in objects, except there we add lots of other stuff. So, syntactically, again, these are usually pretty distinct. You need some kind of way to define a record or a structure, what its name is going to be, what kinds of data it's got in it, and what you're going to call those different fields. And then for access, you need some way of specifying, I want to get at this field inside this item. And ideally, you want that to be something that cascades fairly well. So you can say, I want to get at this field inside this field inside this field inside this field of this item. So those will be some of the things that we consider here. In terms of the operations, most of this should be pretty familiar. Right? Obviously, you're going to want to be able to access individual fields of items, and you're going to want to be able to do things like assign to them or copy from them. And of course, that's usually going to be based on whatever the underlying type is. If I want to get at field A, and field A is a string, then it's going to use string assignment or string additions or whatever that happens to be. What's a little more interesting for us is what happens if I decide to copy an entire record. If I have one record X and another record Y, if I say Y is assigned X, what happens? Does it just copy a reference? Does it do field by field copies? Right? And again, that's going to have implications in terms of how long they take, and it's going to have implications in terms of side effects and whatnot. So that should be fairly familiar. What might be a little more interesting is if we consider cases like this, where I have two structs or two records that have some fields in common, right? At least structurally. Right? Say I've got one structure that's got 3 integer fields in it and another one that's got 2 integer fields. Or maybe they both start with an int and a float. If I try and do a copy between those two, if I say something like an instance of type A is assigned to an instance of type B, or vice versa, is that actually allowable? What happens? Does it simply say, okay, well, what I'll do is, since some of the fields are compatible, I'll just copy those across and ignore the rest? Or does it actually disallow this? Again, that's going to be a language by language thing. Am I able at runtime to actually go through and change the nature of a structure, change the nature of a record? Can I add new kinds of fields as the program runs? Or can I remove fields? And again, there are languages that will let you do this, and of course others that will not. Typically, if you're going to go through and start adding fields or changing the structure of something as the program runs, then you're also going to need operations that let you do things like say, okay, well, let me get a list of what fields actually exist right now so I can access those. So those are some of the more interesting ideas you might run across, depending on your language, obviously. And then there's the whole implementation side. If I create one of these things, where does it live in memory? How is it laid out? So, as with arrays, if we're thinking of these more complex data types, they can wind up either in the stack or in the heap, right? If they're in the stack, then they're taking up all that stack space. If they're off in the heap, then we have to make sure that we deal with the memory management issues that come along with that. If they are resizable, if we can do things like add new fields to it as it runs, then we have the same sort of issues as with resizing arrays, where suddenly the space that's available isn't big enough. And again, if we've got these things stored on the stack, that's probably not going to work, because we probably don't have the ability to easily change the size of our stack frame. If they exist off in the heap, then we have to decide, well, what do we do? Again, do we create an entire new larger version of this struct somewhere and move all its data there and deal with any pointer issues that might come up as a result of that? In terms of getting at the content of a struct, we want to think about what the compiler must be doing, what's happening at an assembly language level if we're going through and trying to access a field. If I say I want to get at x.y, what happens? So typically, your compiler is going to be going through and saying, okay, well, I'm going to keep track of the starting address of each of the structures in the current function, for instance. So I'll have the starting address of x. And I'll also maintain a table somewhere that tells me what the offsets are to the start of each field within the memory space for x. So when you say something like, I want to get at x.name, then the compiler is actually going to say, well, I'm going to stick in a reference here to offset of 27 bytes or whatever it is from this particular address, the memory address where I've got x stored. Now, that does introduce the same kind of memory alignment issues as we discussed way back when in the last of the face-to-face lectures, where we were looking at functions and variables and memory alignment. And we talked about this idea that if I've got an integer variable, and then a float, and then a char, and then another float, does the compiler actually put these things in memory in the order that you declare them? In which case, it has to make sure that they each fall on a memory boundary, an alignment boundary, that matches the rules for that data type. So again, for instance, doubles might have to start on an address that's divisible by 8. Floats might have to start on an address that's divisible by 4. Shorts might have to start on an address that's divisible by 2. There'll be all these memory alignment rules that you have to follow, and if you're sticking things in memory just in some sequence that you declared them, then it has to worry about sticking in extra padding bytes in between so that these things all fall on an appropriate boundary. So that exact same thing happens with our struct. If we look at the case here, where we've got a character, followed by a long, followed by a character, followed by a float. If we suppose that the memory alignment rules for these are chars have to begin on an address divisible by 1, longs by 8, floats by 4, then if we stick the char on some address, then there could be anywhere up to 7 bytes of padding required for us to wind up at an address where our long can sit. The char can go anywhere, so it could sit right after the long, but then again, we might need a few bytes of padding to bring us out to an address that's divisible by 4 to store our float. Or the other possibility is the compiler says, well, if I put the biggest thing first, or the thing that requires the largest memory alignment size first, I'll put, in this case, the long first, and then if it started on an address divisible by 8 and it's got size 8, it's going to end on an address divisible by 8. So it would be okay to stick the float after that. Right? It's an address divisible by 8, it's an address divisible by 4, so we're okay. And then I could put the chars after that. So another idea to save memory space is just to rearrange these things so that they appear in sequence. Now, as a programmer, the only time it makes a difference to us is if we're desperately concerned about the size of our structs, right? If I am really worried about how many bytes this takes up, then I have to keep in mind that if it's storing these things in order, I've got to count the sizes of these fields plus the sizes of the padding inserted in between. Or if I'm doing my own manipulation where on my own I stop and think, okay, well, if I've got my variable x starts at this address and I look 27 bytes down the road, I should find my string field or whatever it might be, then it's important for me to know what the rules are so I know how many bytes of padding I have to skip over when I'm computing those offsets. So I wanted to take just a moment while we're at this point to take a look and experiment with this a little bit. So let's actually play with a little bit of C, and in the directory where I stuck all the code to go along with these slides, you'll see one program. Let's see, the struct layout. So if we go through and take a look at the contents of this, all I've done here is we're just going to go through, create a struct that's got some weird kind of order of data in it, and we'll just look at the sizes of each of the data types, the order they get stored in, and the memory addresses they wind up in, so we can figure out if C is actually storing them in sequence and if it's actually inserting padding and that kind of thing. So this particular struct, if you take a look, we're going to go through and start off in the beginning here. We're just going to start from the largest and go to the smallest. So in theory, no matter what, it should store these things in sequence where they should, you know, the big doubles first, and then the long, and then the float, and then the short, then the char. And then we'll try mixing it up a little. So we'll go from a char to a short and see if it keeps them in the same order or if it rearranges them. We'll see if it inserts padding in between them. And again, then we'll go from that to an int and see if there's padding. Then we'll try going from same sort of idea. We'll start with a char and then go for a float and see if it winds up inserting padding. So just experiment with this a little bit. And so the way we'll do it here is, pardon the great hideous lump of code, but all we're doing is for each of the fields, we're going through and printing out the field, and this is in the same sequence as they were declared in, so we can see if it comes up in the same order. So print the field, then we'll print its address. And all we're doing, all this mess is doing here, is going through and saying, okay, well, here we'll take the address of the field, and I'm just casting it to a void star to be compatible with the data type that %p expects. So here we're just playing with a little bit of data type casting, a little data type conversion. Whatever kind of pointer this is, just convert it to a void star or treat it as a void star. And then for each of these, after we print out its address, we'll print out its size so we can figure out where the next thing should wind up. We'll just do that for each of these beasts in sequence. So let me just make sure that I've got this compiled. Okay, so we looked okay there. So sorry, I've got a bit of lag here. We'll run that beastie. And again, they're appearing in sequence, so hopefully our memory addresses come out in sequence. And so what we see is we're just going to look at the last couple of bytes of the address here. The rest of it should be pretty consistent all the way through. So we're starting off at an address 0. Our pointer should be 8 bytes long, and the next one comes up at address 8. So far, so good. It's 8 bytes long. Next one comes back at a 0. Remember, these are in hex, so it's treated as mod 16. So that looks out okay. And for each of these, we're seeing that the addresses go up appropriately, right? 8 goes to 12, plus 4 goes to 16, so it gives us a 0 again, goes up by just pretty much exactly the way we would expect. 2 bytes takes us up by 2. So all of this whole chunk appears in sequence with no padding in between. Then we start getting into the case where we mix things up. And here, going from our char to our short, you can see that we were on an address divisible by 2. We added 1 byte for the char, and we wound up on an address divisible by 4. So here it has clearly stuck in a byte of padding. Similarly, going from the short to an int, right? We started off on an address divisible by 4. We added 2, and then the next thing we used was an address divisible by 8. So again, it had to have stuck in 2 bytes of padding there. Now, if you were a weird and twisted programmer, you could then go through and say, well, if I know it's doing this, then I can figure out the offset of however many bytes this is from the start of my item to those 2 unused bytes, and I could do something with those if I really wanted to. And as I mentioned, people will do all sorts of weird things like this if they're really scrapped for space. But it is something to be aware of, right? For this particular struct type, there's going to be a bunch of places where you've got extra unused bytes of padding inserted. So, again, I would like you to get used to the idea of, if you want to experiment with how things work, C or C++ are good languages to go through and find out, because you can dig into memory and you can see how this stuff actually works. All right, so that was where I wanted to go for looking at the underlying implementation side of things. Last point that I wanted to look at was dealing with passing these things as parameters or returning them, right, as return values from a function someplace. So this comes back to some of the issues of copying and some of the issues we discussed with arrays, where you're saying, well, if I'm going to pass one of these things as a parameter, do I actually copy the entire thing onto the stack? Right? That means using all of the memory space that's required to do that. It means taking the time to actually do that copy, or the same thing for returning, right? Do I actually return, do I actually copy all of that data from the version that's on the stack or referred to from the stack into wherever it's being returned to? So that's got implications for memory use. It's got implications for runtime, just the amount of time that it takes. Or the flip side is, do we turn around and say, well, that's going to use a lot of memory, it's going to take a lot of time. Instead, how about we just pass a reference to it, pass a memory address, effectively pass a pointer. And that way we save lots of time, right? It happens really quickly. We save lots of space on the stack, right? All we need is the space for that pointer. But it does introduce the possibility of side effects, right? As we've seen in Lisp. If you're passing, in Lisp, since these things are essentially just glorified lists, it's going off and passing a reference to it. And so inside, you can wind up going through and destroying things. So stuff to keep in mind. It does have implications in what you need to consider. Do you need to worry about, when you're using this, do you need to worry about the memory use and the runtime speed? Or do you need to worry about the possibility of side effects? All right, I think that about brings us to the end of the structs discussion. So we'll pick up with a new data type on the next one. All right.